Thank you for the introduction, and thank you all for coming. Let me talk about this new paper, Tour de Gros. Well, new paper. It was released in 2025. We're in 2026 already. So we've heard a lot about surface codes, and let me rehash some of the reasons, why we might consider QLDPC codes. And the main reason is that a surface code qubit requires, say 2 times d plus 1 squared physical qubits. And at IBM, we found these new BB codes, bivariate bicycle codes, of which the Gros code is one example. It has a code distance of 12, and it encodes 12 logical qubits for 288 physical qubits. And the so-called 2 Gros code has a distance of 18, and it encodes 12 logical qubits for a cost of 576 physical qubits. And if we compare that to the surface code, comparable code distances of 11 and 17, then we need 288 or 648 physical qubits to encode just 1 logical qubit each. So, and even if we look at the noise simulations, we see that when we compare to the surface code, we need about 10 times, about an order of magnitude less, fewer physical qubits, but we still have a comparable code distance. And this is like a major motivation for us to study these QLDPC codes because the coding rate is much higher. We represent the Gros code using this torus, and it's maybe a little bit deceptive because we also need these purple edges, the so-called long-range connections, to implement the Gros code. So this picture is from its Tanner graph representation, which relates to what syndromes needs to be measured. As you may have noticed, this picture has a degree 6 connectivity. And IBM devices, they currently have just incremented to a degree 4 connectivity. We have a new device since last year. But in the lab, we have shown that we can build devices with a degree 6 connectivity without too much loss of gate fidelity, which I've highlighted here in purple. And moreover, there's another wrinkle, and that's that these long-range connections are indeed long-range. They're not, so the Tanner graph is not planar, so we need to kind of bridge this distance, not between NISQ and FTQC, but between our qubits. And so in the lab we built devices that also show that we can build superconducting qubits with comparable gate fidelities at these extreme distances of 14 millimeters. So for this experiment, I don't think that was included. Yeah. However, there is an experiment for the out-of-plane connectivity. The graph connectivity required, like I said, is non-planar, so we need to kind of hop over other edges. So to do that, what we added was this, I'll just use the mouse, this second level of connectivity on top of our existing planar connectivity. I hope you can see the little red highlighter. And that allows us to connect, qubits that are not in the same plane. And even there, our testing shows that the gate fidelity is comparable to an interaction that was just in the same plane of the device. So this red highlighted thing is a gate being performed between qubits that goes up through the higher level and then back down and connects to qubits. Yes, question?
What's the purple number is?
The purple? This purple is the gate fidelity?
So if you go back to previous slides, seems like when you have the short term, the short distance gates is actually bad and then getting better. So it's like if you look at the distance versus the gate fidelity, it's not like uniformly increase? Like,
Yes.
do you have like explanation? It is like an engineering thing, or?
Well, I'm not an experimentalist, so I can't tell you exactly why this behavior was observed. But the main takeaway I would like you to have is that either we have a short range connector or a longer range connector, the gate fidelity is comparable.
So in these demonstrations, was it with you had a connectivity of Q10 to like 300 qubits plus a long range, or was it just the long range by itself?
Yeah, I'm not sure. Sorry, yeah. Oh.
I mean, neither of us are experts on the experimental side, but oh dear. This particular experiment, I think, was not hundreds of qubits, but just a few qubits of different lengths, and that also explains the kind of disorder in the error rates. They had different frequencies, but they were all together. It wasn't like they systematically built different sizes separately and
No.
But do you remember whether this had degree more than one? Was it just degree one, just connect?
I don't want the clicker. Sorry.
It's a good question. I don't know, but if you just look at this figure, you can notice that they're all disjoint, right? Q1, Q2, Q3, and Q4. So I think probably they were not.
Okay.
It was probably like degree one. That's my guess, but I actually don't know.
Thanks.
Another question?
Are there, so ignoring the long range ones to sort of give the degree 6 stability, do you enable like the toric connectivity in the same way?
In the plane, you mean?
Yeah, so do you have a plane of qubits, but then obviously you see the toric connectivity to connect kind of corner to corner? Is that done in the same way as the
well, so the Tanner graph tells us how the qubits need to be connected, but it doesn't have to be how the device is fabricated. We just need the qubits to be connected in that fashion. So no, the graph, it's not necessarily the same. The plane, the torus is not necessarily the planar layout, and then the purple edges are not necessarily the long range jumps. I hope I understood your question. Yeah. Okay. I'm going to try to touch my computer very gently. I think I got my USB port wet at some point, and now it's very finicky or something. Okay, so the long-range connections allow us to build these bivariate bicycle codes, but sort of another benefit of a qualitatively different kind of long-range connection is that it enables modularity. And the modularity is extremely important for us to be able to build these devices because, compared to the monolithic surface code hardware, which was sort of the standard in the literature, you would need to fabricate an enormous chip which has a vanishingly small probability of success, without any failures. And therefore, we would like to have instead many smaller chips, each of which we can fabricate with maybe some high enough constant probability, right? And then we will connect those together using long-range connections, those squiggly green lines, and that will enable us to scale our architecture to larger and larger sizes. Yeah, so two benefits from long-range connections. And so before I dive into what the architecture is capable of, let me whet your appetite by showing, or rather, I'll show you what it is capable of, and then I'll show you how we actually achieve it. So so let me sketch out sort of the trait space here with logical qubits on the x-axis and the T count on the y-axis, and then we have a dotted region here that roughly expresses what quantum computations we cannot simulate classically, and we kind of arbitrarily set that at 75 T gates and 75 qubits. Of course, there are special cases, but so within that region, we find the scientific toy models. One particular instance is the 2D 10 by 10 transverse field Ising model. simulation that we'll look at later. And of course, there are many more such toy models of interest. And then there's the region of cryptography. And finally, we have a region where we can do quantum chemistry. And these require fairly large numbers of T-gates, certainly larger than our initial estimates show our capabilities. But let's get started. So let's say you give me 5,000 physical qubits, and each of my physical qubits has a noise rate of 10 to the minus 3, let's say. Then in red, I highlight the capability of a bicycle architecture using gross codes built using these qubits. And if I compare it to a comparable surface code architecture, we see that instead of having, let's say, 50 logical qubits, we now have over 100 logical qubits to perform our computation at an equal amount of T-gates. And I'd like to say, T-count here means including arbitrary Clifford gates in between, right? So we've compiled away all the Clifford gates. And now if I increase or decrease the physical noise rate of our device, then we have a jump in the number of T-gates that we're able to perform. Now we're suddenly able to do above 10 to the 5 T-gates in our circuits. 4 orders of magnitude higher. And the comparable surface code architecture only has about 20 logical qubits. Next, if we switch to the 2 gross code, which has a code distance of 18, so it's much better protected against errors, and you give me 50,000 physical qubits at an error rate of 10 to the minus 3, then we have an architecture of about 800 logical qubits, and we can do about 1 million T-gates on this architecture. And the comparable surface code architecture with the same resources has about 50 logical qubits. And we can do the same exercise. We can decrease the noise rate. Now we experience a jump of almost 10 orders of magnitude in the T-count for 1 order of magnitude decrease in the physical noise rate. And then if we increase our number of physical qubits by 10x, we get about a 10x increase in the logical qubit count. And in all of these cases, we see an advantage over the surface code architecture in the number of logical qubits. Question?
Yeah, so obviously, right, clear advantage on this graph. But I wanted to ask, are you sacrificing runtime by increasing your logical cycle time by moving from a surface code to a bicycle code in this context?
Yeah, like the wall clock time will be slower.
Do you know roughly what the ratio is there?
Well, it's about an order of magnitude. I think that's fair to say. Yeah, another question?
I guess we were chatting about this last night, but let's see, how do I say this? Are the logical error rates that you're assuming here coming from like memory numerics, or are they coming from like lattice surgery?
Yeah, so they come from all kinds of operations, including idle noise, right? So memory noise, as well as the logical operations that we perform. And I will show you later a table of the noise range for each of these kinds of logical instructions.
I guess I meant, so when you're saying like the logical T count that it could support, I'm assuming that that's coming from what logical error rate this code is realizing. Is that correct?
The T count it supports comes from running a benchmark and then calculating what the noise rate is. I will also have a slide on that.
So then are these based on just assuming memory, or are they taking into account the logical error rates of like lattice surgery?
They will take into account both the memory noise rate and the logical operations. They also contribute errors. Yeah. Any other questions? Okay. Okay, so let me start explaining what it means. What does a bicycle architecture mean? Because a gross code is just a memory, right? Like we can just store information in there that doesn't allow us to perform any computation, except for some, trivial Clifford circuits. So what we can do is we can attach an ancilla system that we call a logical processing unit, or an LPU. And by connecting these logical processing units through a so-called bridge system, we can perform joint measurements between two adjacent code modules. And if we connect a bunch of these code modules together through bridge systems, we can build our so-called bicycle architecture. And of course, we will need a way to perform non-Clifford operations. And the standard way we use here is to attach a magic state factory to our chain of code modules through a universal adapter. And this magic state factor will inject the necessary magic states into our computation.
Sorry, one quick question. So,
Okay, sure.
So what does a universal adapter mean?
Yeah, so the universal adapter is a technique developed to connect two different kinds of codes together to be able to perform a joint measurement between two different kinds of codes.
Does this work for arbitrary two codes?
Yeah, I'm not too familiar with the exact assumptions, but it suffices to say on the left side here we have something like a gross code, and on the right side we have something like a surface code, and we're able to do a joint measurement between the two using this universal adapter construction. I have some qubit counts later, but in this particular case, the universal adapter is particularly simple because the surface code is really easy to read the logical operators out of. Another question?
Yeah, does the adapting cost you anything? Like you need to use qubits to do it, or
Yes.
you have something else?
Yes, you need qubits, and of course you need to do some dynamic thing. It doesn't happen for free. There's some circuit that needs to happen.
So there's qubit cost and fidelity. Yeah.
Yes, so there's an associated logical error rate to doing an operation over one of these adapters. Questions?
Does the adapter change the connectivity you need in the hardware?
So the adapters here, I guess part of it is integrated in the logical processing unit that sits in each of the modules. And then there's a connectivity between two adjacent modules that can be provided by so-called L couplers that give us the long-range modularity needed between modules.
Is it still like degree 6 coupling, or it increases beyond this?
Yeah, so to attach the logical processing unit to the code module, we need to increase the degree by at least 1. And in fact, one of the authors, Ted, has worked really hard on decreasing, limiting the maximum degree, and I think we have 1 qubit that has degree 8, but the rest is 7 or lower. Yeah.
I think maybe similar, but then I assume that means that both the logical processing unit definitely, and maybe this adapter as well, are plugging into like the middle of your chip, right? So it's like a 3D integration type stack as opposed to just boundary connections.
Well, again, I can't say too much about how it will actually be built physically, but the connectivity is indeed, you could imagine it as an ancilla system that has wires going into the code, into the bulk of the system. Yeah. Another question.
It seems that like the code is like something relatively well understood, right? But this ancilla system seems like it's up to change. Like, do you really fabricate it, or like there's some sort of interface you can slot it in and change design and slot another one in?
Well, the logical processing unit here is new, and it's still under development, so it could change by the time we build the device, but unclear as to how it will change or if it will change. and what kind of modularity we need. You know, if it needs to be slotted in or out, I can't say. Okay,
Sorry.
maybe last question for this slide.
Sorry if you said this, or if this is a dumb question, but is there some reason you can't use a bicycle code to do the magic state factoring? The fundamental reason you have to have this disjoint?
Oh, well, there are certain code families that are particularly suited to do magic state distillation. And I suppose a BB code is just not one of those. So it's you know, it might be complicated to figure out how to do magic state distillation in one such code. An additional reason, maybe more importantly, is that we have these codes to store our data, so we can't just like wipe the data to make our magic state in the code. Right, you need some scratch space to initialize a bunch of physical T states and then distill, post-select, etc. Yeah. All right. So let me proceed a few slides before I take further questions. So these L couplers are great. We can connect you know, various code modules at longer distances, and in fact, we built in the lab a demonstration of these L couplers that show that over an interconnect of about a meter, we have a 96.5% fidelity. Now, to count the number of qubits in our architecture, let me put up a table very soon. But the architecture that I showed you so far has a connection that is linear. So we have our codes and their associated logical processing units, and then they are connected through these adapters A, and at the end we have some factory F with its universal adapter A prime. But of course we could connect the architecture in a different way. So one illustration here is that the codes are connected in a triangle, for example, with some factory attached at the end of things. And of course we can imagine many different kinds of layouts as enabled by these L couplers. So the actual qubit counts are, you know, maybe slightly less important. I mean, the order of magnitude is important here. We see that, you know, the order of magnitude for the LPU is sort of slightly less than the code system itself. The adapters are relatively insignificant in qubit counts. And then the factory module, the size of this depends on what the physical error rate is of your system and the targeted logical error rate of your T states. You know, so in particular for the 2 grows at 10 to the -4, we're looking at an error rate that is so small we need some distillation factory. So, you know, take this number with a slight grain of salt that these numbers are not like optimized for our particular code, but you know, if we're in this regime, we're doing really good, right? 10 to the -4, 2 gross codes. Okay, so let me present, you know, the logical instructions that are possible in this architecture. And if we assume a connectivity that is, you know, as in a triangle connectivity, so we have a connection from this first module to the third, then we can perform a logical circuit that is depicted here on the right, which contains 4 different kinds of instructions, only one of which is actually unitary. So most of the evolution in this architecture has to happen through measurement-based computation. And the first such measurement is a so-called in-module measurement. And we're able to measure qubits 1 and 7 in a module with an arbitrary polystring. The second thing we can do within a module is 6 types of automorphisms and their conjugates. And these automorphisms act symmetrically on the first 6 and the second 6 qubits. Third, we have intermodule measurements over the adapters that have a limited set of 4 qubit measurements that we can perform. And finally, we need a way to inject magic into our architecture. And we can inject magic in any basis on an adjacent code module. And you know, we suggestively made these boxes wider or smaller to suggest that the time, for each of these operations might be somewhat different. This is not to scale, so don't take it. Yeah, question?
What does 5 mean?
What does what mean?
5 before the. Is it
Oh,
one
it's a
row?
register of 5 qubits. It's just a compact way to represent the 12 qubits that are contained in one code module. And we've pulled out qubits 1 and 7 because they're special in a certain way, because we are able to measure those directly through the LPU system. The LPU system is probing these 2 qubits. Any other questions? Yeah?
Maybe explain what's the subscript of U?
Subscript U?
Subscript of U.
Oh, yeah. So there are 6 kinds of automorphisms, and this is an index from 1 to 6. Yeah.
And those automorphisms are all Clifford?
Yes, they're Clifford. In fact, they're CNOT circuits, so it's even more restricted. Question?
Do you have a rough sense of if you tried to compile an arbitrary Clifford in one of the blocks using those automorphisms, how many of them it costs?
I guess, yeah, that's a good question. To compile an arbitrary Clifford in a block.
Or maybe to change into an arbitrary basis for the measurement.
So I think it's slightly the wrong question because most of the computation is measurement based. We need to have an ancilla in the block. So really, you should be asking yourself, how much does it cost for us to compile an 11-qubit Clifford in a block? Because 1 qubit we don't care about, it's an ancilla. And then we have an answer to that question on a later slide.
Let's pretend I asked that better question.
Yeah, very smart.
Is there, but roughly what is it?
It's roughly, what was it again? About 18 measurements for conjugation, so 9 measurements. And yeah.
Can you help me understand so you said that the automorphisms are symmetric in the first 6 and second 6 qubits?
Sorry, I need to correct my statement before we continue because so the number I said was to conjugate some Pauli measurement. So we can map any 11-qubit Pauli string to any Pauli string we want, or rather we can measure any Pauli string we want with an overhead of 18 measurements. That doesn't mean we can do any Clifford operation. Sorry for the confusion. Yeah.
That gave me time to think about how to word my question better.
Yeah, no problem.
So can I use shift automorphisms to arrange any pair of the 12 qubits into positions 1 and 7? Or do I need to do something more complicated to do, in general, a measurement of 2 arbitrary qubits within a block?
So the shift automorphisms, they're not simple permutations of the logical qubits. They perform some kind of complicated CNOT circuit. So the structure of which is not well understood. I have an open question slide about it. But it's not as simple as saying, okay, I want to measure qubit 2, so I'll do 1 shift, and then I'll measure qubit 1 or something. Yeah.
And shift automorphism is the same thing as these U's?
Yeah, that's the U. Yeah. Okay, last question.
Okay, so if I understand correctly, and I've read the paper, so maybe I'm just trying to ask you this question for my own understanding. The measurement, the ZII, and then the shift automorphism, that doesn't give you all measurements. Then you have to repeat. May have to repeat that those 2 things together some number of times too, right?
The measurement is the U. You mean the UI?
If I want to do an arbitrary Pauli measurement on a block, right?
Yeah.
So I have to compile that down into some number of instructions.
Yeah.
And I compile that down into groups of these first measurements, which you call the TMs. plus some shift morphism, and then
Yeah.
those two things together, I repeat that some number of times to get some arbitrary thing.
Yeah. So yeah, through measurements we affect some Clifford rotation in the module, and that Clifford rotation will allow us to measure arbitrary Pauli strings in a module.
Okay. I understand that. I was just trying to figure out like what was repeated, what needs to be repeated to do that, right?
I have the construction in the slides. I don't know if I will have time, but we'll see. Yeah. Okay. 10 minutes. Wow. Okay. I'll skip this because Michael's going to talk about it in the next talk. To get logical error rates, we pick our decoder, relay BP, go to the next talk. And this decoder has a certain logical error rate associated to it when we perform logical operations on our code. But if we want to figure out what the logical error rate is for very low p, it's actually quite hard to sample this regime because we need tons and tons of samples to determine that the logical error rate was, say, 10 to the minus 11. You need 10 to the 11 samples to even get one error to show up. So how do we figure out what happens at low p? We developed this new technique, or rather Michael and others, which extrapolates from so-called low-weight failure fraction. And what we do is we pick a certain number of errors to occur in our code, and then we see if our decoder fails for this number of errors, and we count how often this happens. And through a certain ansatz function, we can fit this function here and map this back into a logical error rate. And then we can check from Monte Carlo sampling that this actually corresponds to the error rates that we get from the sampling. And now we can just read off for our p-values what the logical error rates are. And this is for the gross code, and this is for the to-gross code, where we're not able to simulate some of the more complicated operations in time. And I tabulate these in the table here, which you can find in the paper. However, we've been working on improving the worst offender here, which is the gross code at p is 10 to the minus 3, and this is actually improved to 10 to the minus 4 now. We need to, rerun all the capability estimates, etc. So please look forward to a version 2 of our paper coming up in the future.
What did you change?
Well, there were some bug fixes and other, further studies of the noise simulation. But I will leave that to the paper to explain in further detail. I'm not going to, in the interest of time, explain too much about how to compile for the architecture. This is a summary picture that you can also find in the paper. But you can also just download the code on GitHub. It's publicly available. And this will allow you to skip all the following slides. Ta-da! We did it. I hope I'm not going too fast.
Sorry, can you just jump back for just a second so I can see that we have some different classified all your measurements, so you're doing an arbitrary basis measurement with this P file, and then, okay, let's go.
Yeah. So we had a short discussion from a question of how to measure an arbitrary Pauli string in our module. And this actually shows up in the circuits that we want to perform in the compiler. And in particular here, for this circuit, the Y-tensor P1 measurement is not a native instruction that we have available to us in the architecture. So what we do instead is we conjugate this P1 Pauli string with some 11 qubit Clifford gates so that it does become available to us within the architecture. So we find some Clifford rotations that use this ancilla qubit here. We use this notation triangle to mean that it's trashing. It's kind of like using this ancilla here, measuring it out in various ways. to implement a Clifford rotation. And each of these Clifford rotations are fairly easy to implement using 3 measurements. And there are various equivalent circuits to do that. But of course, all these Clifford rotations do give us an overhead for reading out some polystring for some measurement. And this overhead we plot in this histogram here on the left. So what we basically did was we did a brute force, like a breadth first search for all the ways we can conjugate polystrings with Clifford rotations, and we get all the 4 to the 12 polystrings out this way. And then we see, oh, okay, on average, this takes about 18.55 measurements to measure some polystring. But in the practice, we can also optimize over the ancilla qubit because we don't care the basis. And then we save a grand total of 0.1 measurement on average. Awesome. Yeah, and it does make the code more complicated, sadly. But so the open question is understanding the group structure of the automorphisms so we can reduce this overhead. Because we have 15 times 6 squared easy measurements available to us, which gives us 510 so-called easy or native Clifford rotations. And the full poly group is 4 to the 12, which is quite a bit larger than 540. So if you give me like a bunch of these poly measurements that we wish to perform, can we map each of these measurements to some easier form by conjugating with a shared Clifford rotation so that all of them become easier? So that's an open question I thought fitting for kind of an applied math workshop. Yeah, so to continue on, we saw this figure about the capability estimates.
So for that question, the goal would be to basically batch your measurements.
Yeah, so this would allow us to, batch the measurements. Like I have a circuit and I see all upcoming measurements, and yeah.
Just one point, like the starting point here is that you can measure any polystring on one cell. And then you have this, this permutation is available, and then you want to ask, how do you combine these two to measure any polystring?
I think it's noticing that we have quite a bit of structure in the circuits, i.e. we need to do a bunch of measurements in a row, and instead of doing the Clifford rotations for each of them, maybe we can do some Clifford rotations for a set of them, and then each of them will become easier. Think of diagonalizing a bunch of matrices, right? Like, if you have a bunch of commuting matrices, maybe you can just like make all of them easy in one go. Yeah. Okay, so how did we get these capability estimates? Well, we just did some random poly-based computation. So what we do is we set the T count for each of our rotations to 1, and we pick a random polystring, and then we add up all the logical error rates from our table by counting the number of gates. And this also includes the idling for each of our modules, because we know how long an idle cycle is and how long our modules are not doing anything. So each of these also add an idle instruction. The resulting table is this. I don't have a lot of time to go into this, but suffice it to say, we say that the circuit fails if our error failure probability exceeds 1/3. So we can amplify the success rate by doing some kind of majority vote protocol. Another benchmark we looked at was the 10 by 10 2D transverse field Ising model. The circuit has 1.8 times 10 to the 5 poly rotations. And here we solve, say, for the physical noise rate that is required in the architecture to be able to do this algorithm. So we sample at various p rates. We sample what the circuit error rate is, and we plot a fit to these points. And at the intersect, we see that if I build an architecture using gross codes, we need a physical error rate that is at most 2.1 times 10 to the minus 5. The comparable surface code architectures are as follows. So for distance 7 and 9, we get different p-values. But I would like to note that, of course, the qubit count for these architectures is much larger. And if we use 2 gross codes, which have a much larger code distance, but also require some more qubits, so about 8,000 qubits, we need a physical noise rate of at most 7.3 times 10 to the minus 4, pretty close to 10 to the minus 3, if I say so. And the comparable surface codes have a distance of 17 and 19 and require more than 60,000 physical qubits. So to conclude, we have built a bicycle architecture that satisfies, or we have proposed a bicycle architecture that satisfies our 6 sufficient criteria for a scalable fault-tolerant architecture. The first being obviously that it's fault-tolerant. The second is that we can address any qubit and measure it. It's universal in the sense that we can perform a universal quantum computation. It's adaptive in that we can do feed forward and adjust future computation based on measurement results. And it's modular because we can replace individual modules and build a larger architecture. And finally, it's efficient in the sense that we can execute meaningful algorithms using only reasonable physical resources. So as a future outlook, there's obviously the time overhead question that I briefly showed to you, but we would also like to look at other models of computation that increase the parallelism available to us. Right now we have only one magic state factory, and this can lead to circuits that are quite slow. But having more factories would mean updating our computational model to make use of that additional parallelism. We would like to improve our decoders. We are very interested in other kinds of QLDPC codes that make use of these long-range connections, now that we have shown that we can build them, including also different kinds of magic state factories. And finally, this can result in us changing the bicycle instructions that are available in the architecture. Thank you so much for your time, and I'll take questions.